Look, this question is really straightforward. Let me show you. So this is the original definition of the gamma function, right? And the question is asking to prove, this is number 6. The question is asking to prove d over dp of gamma p equals 0 to infinity x of p minus 1 e to the minus x ln x dx. That's what we're supposed to prove. Okay, all we have to do is take the derivative of the green definition of the gamma function, the definition in green, with respect to p. Okay, so this is dp. This is d over dp of the integral of x to the p minus 1 e to the minus x dx. Now in calculus, as long as the function is continuous from 0 to infinity, I could go with the derivative inside the integral. Yeah, so I could say this is the same thing as 0 to infinity d over dp d over dp of x to the p minus 1. Now, e to the minus x and ln x don't have p in them. So as far as the derivative is concerned, they're constants. I can just put them outside the derivative. Let me just move these a little bit to the right here. Okay?
Yeah.
And so, and then there's a dx here. Oops, ln x. Not far enough. Let me move them a little bit more. ln x dx. Okay, so the derivative is only with respect to the last term. And what's the derivative with respect to the last term? It's like I mentioned to you here, the derivative of a to the x is just a to the x ln a. So this becomes e to the minus x ln x. And the derivative, now x is the constant, so you will get the same thing back multiplied by ln of the base. Who's the base? X. So you get ln x dx. So this is straight from the definition. So this is d over dp of gamma p. And you would have proved it in like a couple of steps. This is what they're asking you to. Oh, okay, I repeated the ln x here. There's only one. Wait, where did I get this ln x? Hold on. No. Sorry, there wasn't an ln x here, right? There was just e to the minus x dx. And so the ln x comes from the derivative of x to the p minus 1. I just miswrote it there. So this gets you this.
Yeah, I see that.
Right? Okay, and now it's asking you to prove that the nth derivative will get you the same thing except ln x raised to the n. Well, it's sort of the same thing. If you repeat this thing on, if you were to take the second derivative, well, if you repeat that same process one more time, it's the same thing. You're going to get e to the minus x times ln x, and the derivative of x to the p minus 1 will be x with respect to p will be x to the p minus 1 times another ln x dx. So I could just move this and make this square. And then if I take the third derivative, I'm gonna get ln x cubed. And if I keep repeating this n times, notice the only thing that's changing is when this is the second derivative, you're getting here a 2. When it's the third derivative, you're gonna get another factor of ln x. Fourth derivative, fourth factor, and so on. So when you get to the nth derivative, right? When you get to the nth derivative, you're just gonna get ln x to the p. To the n, I mean. 0 to infinity, e to the minus x, ln x to the p, to the n, x to the p minus 1 dx. So this proves the second equation. Questions on that?